streaming also. Okay. Yeah. Good afternoon, everyone. This is welcome you all for the third session of the fourth day. We have with us Dr. Sushil Thale, who would be delivering his lecture. Before he starts with his technical session, I will give a very brief introduction of him, although he has got a very vast experience, which he will be sharing during his lecture. So I'll just be briefing you about his academics part and some part of his research. He completed his PhD from Department of Electrical Engineering, IIT Bombay, in the field of microgrids and power electronics and power systems group. He received the prestigious POSCO Power System Award 2016, instituted by Power System Operation Corporation and FITT IIT Delhi for his PhD thesis work. Before completing his PhD, he received Diploma in Electronics from VJTI, B in Electrical Engineering from Sardar Patel College of Engineering, Mumbai, and ME in Control Systems from VJTI, Mumbai. He worked with Siemens Limited, Thane, before joining Father C. Rodrigues Institute of Technology as lecturer in 1995, and currently he is the Dean of R&D and Professor in Department of Electrical Engineering. He is also the Chairman Board of Studies in Electrical Engineering at University of Mumbai. He is a senior member of IEEE, editor of IETE Journal of Research, a fellow of ISLE, that is Indian Society of Lighting Engineers, Institute of Electronics and Telecommunication Engineers, and Institute of Engineers. He is a member of SAE India and ISHRE. And these are just not to name, but he is actively involved in all the activities of these professional bodies. He has published over 50 research papers in IEEE transactions, journals, and IEEE conferences. He is a reviewer of IEEE transaction on smart grid, IEEE transaction on power electronics, IEEE transaction on industrial electronics, IEEE transaction on industry applications, etc. He is also working as technical consultant for several companies in electrical engineering, solar PV, and lighting industry. He is also a certified energy auditor by Bureau of Energy Efficiency, Ministry of Power. He teaches courses on electric vehicle technology, microgrid and smart grid, DSP application in power electronics. His research interests are power electronics, renewable energy, and energy storage system. He is currently guiding 5 PhD students in the fields of electrical vehicles and microgrids. He is co-founder and director of Navi Tech Solutions Private Limited, which is actively involved in electric vehicle technology development. This was a brief introduction of this personality. I would now request Dr. Sushil Thale to take over and start with his lecture. Welcome, sir.
Yeah, thank you very much, Dr. Aqleem, for the introduction. This is after lunch session, so I'm a bit doubtful about the alertness, but I hope I can take my sessions such a way that some questionnaires at the end of the presentation I'll expect from the attendees. So I'll start with my presentation. I think I have to go for present, where I have to click. Okay. Okay, I hope the presentation is seen.
Yeah, it's visible, sir.
Yeah, thank you. Okay, so I'll be talking about the electrical vehicle drive today. Exactly not in the details by which I can be able to tell you how to calculate the components and the subsystem requirements. But we'll look at the overall view in which the electrical vehicle power drive, the inverter drive is been designed, and we'll have some discussion in that regards. Okay. As Dr. Aqleem told you, my major work was in microgrid and more in the renewable side. So almost for 15 years I was working in this domain and completed my PhD also in that same domain. But last 4 years I just diverted a bit to the electrical vehicle side, looking at the kind of research going on in this particular domain, and a lot of application regarding electrical storage and subsequently renewable energy will be coming into picture in this domain. So it's more like a interdisciplinary in the nature, not only from the electrical engineering side, mechanical engineering, computers, almost every domain is involved in this case. So lot of collaborative efforts will happen here, and that is how I witnessed that this particular domain will be helping all of us, not only a particular branch of engineering, but everyone out of us will be able to contribute something or other. Okay, so we'll look at what we'll be discussing now in this particular session. My focus being from the power electronics group, my focus in this presentation will be more on the power electronics subsystems and component selection. What is the basic guideline? What are the considerations to be given while designing the electrical vehicle drive? So when I talk about electrical vehicle drive, it primarily going to include the power inverter, the inverter which is the main inverter of the EV. That will be discussed more in detail. Whereas motor types, motor selection, I think you must have had one session on that. Regarding the battery management system, I am sure Dr. Sheldon Williamson must have talked to you. So you must have had some background about all other components. Now I am going to talk to you about the power inverter design. Okay, so my outline of the presentation will include the EV drive subsystems, stages in the EV drive design, okay, factors affecting the EV drive. So here when I say drive, it will include both motor, battery and your inverter together, okay. And then subsequently we'll divert into EV inverter components and what are the challenges and what are the considerations to be given. And I'll be briefing you not much in technical detail, but more on the explanation part of it, the ongoing work of EV inverter design in our lab and other activities in EV domain at FCRIT. Okay. So if you look at this picture, which shows the basic ingredient of electric vehicles, if I could have seen this picture maybe a few years back, okay, it could have been more on the IC engine side, and microcontroller, microprocessors are ingredient of that, controlling the engines and other auxiliary components of IC engine based vehicles. Okay. But now if you open up any electric vehicle, what you see is all electronics around, all energy storage around, motors and so many other things which are going to be there. So if you see the picture from the top, what I'm going to see is more of the electronics, more of the software, more of the storage, more of the electrical components, okay, integrated together to the chassis, and possibly we are getting the function done by IC engine. So here this picture tells you about what all electronics are going to be included in that. All are important. External to this car, external to this vehicle, the chargers will be there. Chargers will be fed from the AC mains, so and so. So if you go outwards, there is electronics involved. There is electrical things involved in here. Here, if you see the vehicle, okay, this electronics mainly focus with power electronics as a major application domain. So onboard charger, DC-DC converter, EV inverter, okay, then the BMS battery pack, the AC compressor converter, everything is going to include some form of the power electronics. And to control their power electronics converters, okay, of different form, you will require the controllers, okay, controllers with the software and software with a control implementation in the form of the realistic control we talk about. So this combination basically going to deal with lot of electronics component, large number of electronic components integrated together to act to give a particular functionality, and to when they get integrated, they are going to work in a way that the vehicle will be running the way we are expecting it. Okay, so this kind of an integration is going to be quite complex, because every system by itself is a lot of R&D is required to be going into this direction. For example, if I talk about only onboard charger, there are companies who are only involved in onboard chargers, and a lot of research going on in onboard charger. I hope Dr. Prajaf Prabhakaran must have spoke to you about this. Is what I am hoping so. So onboard chargers are the one which is supposed to charge the battery, and subsequently back up the EV inverter for driving the electrical motor. So right from 2.2 kilowatt to almost 10 kilowatt of capacity is the onboard charger, with a very small footprints which are there on the onboard, is also part of this EV. DC-DC converter for converting a high voltage pack to a auxiliary battery charge requirement, and therefore pumping the auxiliary power requirement for all the electronics on board, is also a critical component. Okay, so when I'm talking to you about all these other components, is they are also critical to make the EV inverter run, for which I'm going to talk to you about. So DC-DC converter giving the auxiliary battery supply charging conditions. So this power supply, this converter also is going to be critical. And naturally, these are all going to be sealed. These are all going to be packed in a small footprint, and therefore the designing of these components or these subsystems are also critical. So as much as importance is given to the EV inverter, there will be as same importance will be there for the rest of them. BMS played a big role as far as battery performance improvement is concerned, and quite a bit of interaction between all these components together with the EV inverter happens all the time to make sure that the overall impact of the vehicle is going to be really fantastic compared to the existing IC engine based vehicle. When I'm saying so, I'm just wanted to make you alert on this that IC engine vehicles are not bad in the context of the design. Not, in fact, they are matured enough. They are fantastic in their nature. Only thing now we are replacing them with EV just for the sake that petrol and diesels are not there. So don't take me wrongly on that direction. That IC engine vehicles are bad and what we are talking about EV is great. No, we want to replace the petrol and diesel with suitable renewable energy supplies and battery packs, which will make sure that it's going to be an less polluting, and therefore we will be able to survive for the more time with this transportation areas. Okay, so this context of making all electronics, all electrical coming together, okay, is going to challenge us to work together because when I think of a capacitor, okay, as simple as that in electronics, when I want to use it in EV domain, okay, the things are quite different in that case. Okay, so how that these are going to be different, we'll look at some of the discussion on that, right? When we take everything together, for example, if I'm talking about SUV kind of a vehicle to be designed, right? All these components are going to be large capacities. For example, main battery pack can be of the 30 or 40 kilowatt or even more than that. Okay, 40 to 80 kilowatt hour battery packs are being used in many of the EV which are commercially available. So similarly, the EV inverters are going to be designed from 150 kilowatt to 200 kilowatt or bigger size with a very small footprint. Okay, the specific energy density or specific power density in all the cases are going to be really high, and that's what it is going to put more challenges to cool these components to ensure that the temperature remains in the limiting conditions, and therefore operations can be guaranteed under all situations. Electrical motors, when they are interfaced with a particular type of EV inverter, they are required to be controlled differently. But in principle, I can say that whether it is a PMSM motor or whether it is induction motor, or for sake we can say about even BLDC motor, when I want to work with that, it is inverter which is going to drive in principle. So this I'll not categorize EV inverter to be used for BLDC or induction motor or so. I'll just say it is inverter, a three-leg inverter, so that in principle we understand the operational requirement of it, design consideration behind it, and finally we will be talking about specific about few challenges associated with that. So we'll not really go into more details which motor, which kind of inverter it will drive, what kind of control it will be talking about, and how we are going to implement. So our focus will be a three-leg inverter to be designed, and for doing so, what are the challenges we'll be having, and how to resolve the challenges while doing the actual design. So this design required to be supported. These components or subsystems are required to be supported with a very good thermal management system. Okay, most of the times we'll find it out कि larger size capacity vehicles. Thermal management system is a liquid cooled system, and for a smaller EV like a two-wheeler or three-wheeler or so, these are cooled naturally, or these are cooled with sometimes with the forced air cooling. So this thermal management system also is a very important component of this EV design. Okay, required to be dealt very specifically, and they have to be in conjunction with all the components taken together. That means if I say that my liquid cooling network is pumping the liquid into the electrical motor, okay, it will have certain LPM, the flow rate which is available. the same liquid after certain amount of cooling will enter into the inverter drive and then get heated up and then come out, and so and so. So the same network is being continued for sharing this particular liquid which is flowing out of thermal management system, and ensure that all the components, all the subsystems work under a given constraint operational temperature limits. So the coordination, control, overall supervision, overall thermal management system, if you take into account, there are a lot of logistics as far as communication is going to happen between all of them. So on the, if you see the overlay of communication network on this whole picture, okay, each one of them will be talking to each one of them in a way. I should say that they talk to each other all the time, and to optimize the result, this communication are going to be a critical thing, and based on that communication only the whole operation of this complete system is happening. So there are a lot of new communication protocols which are being implemented in this kind of category of vehicles. One of them which is very commonly used, the control area network, that is CAN. Okay, so CAN is very popular in conventional IC engines based vehicle also, but it is also playing a part in EV in a big way, and there are other protocols also available along with that. So with this overall picture, you might have been, I'm sure that you might have been aware of it. I'm sure some of you must be working in this area, or must be working much in the deeper way in some of these areas. So your understanding, your knowledge on this must be very, very good. With that as a background, I'm just talking in the context of some of you may not have a complete idea about what is the EV that it is going to work. So bear with me for that reason. I'll be talking in general also sometime. So with this picture in mind, let us go ahead and see what is there in EV drive. So EV drive, when I'm going to focus it, I'm in principle going to focus on this section, EV inverter, which is going to drive electrical motor. So electrical motor is going to be there as a load for the EV inverter, and the battery pack is going to be the input for the EV inverter. And other subsystems is going to take care that the temperature is going to be within the limits. Okay. So let us look at what are the basic starting point for us to think about it. When I think of the EV power drive, I include the electrical motor, inverter, thermal management system, control and communication, and some other auxiliary subsystems which will be part of this complete integration. So electrical motor, I think you must have gone through these sessions earlier. Inverter, bit of it we'll talk it today, talk now, and thermal management system will be out of scope for this discussion. Some discussion on control and communication we'll have it, but major reason of discussing this here is the how these designs are going to be primarily affected, and why we should do it at our end now within our country. So let us look at the cost split, or I can say specific cost related to these major components. So when I talk about electrical motor or electric motor, okay, it comes out to be roughly, this is not very grossly true in all the senses, but generally if you see the commercially available components, if you want to just take something out of market and use it, okay, it comes out to be roughly around $10 to $12 per kilowatt. That means if I want to just take a 100 kilowatt motor for driving an compact SUV, okay, then in that case I'll require something to shell out, say like 90,000 to almost 1 lakh rupees approximately. This number can go high in a specifically featured equipment like manufactured by some other companies with a very small footprint. They allow you to have 100 kilowatt motors also available, making the system very, very small, compact, and but naturally the cost of those electrical motors are very, very high. But in general, if I want to go and buy it from the market, I can think of something like a lakh rupees to be invested for a 100 kilowatt motor. These are very small size motor compared to conventional motor available in electrical side, which are used for the other purposes. The main reason behind making it very small is that we are using the liquid cooled motors, and therefore the size becomes smaller automatically. So the size becoming smaller, the material used in that motor also is smaller. Inverter, what we are going to talk about, is also in the same range of $12 to $14 per kilowatt, and therefore it will cost you something between 1.25 lakhs or so for 100 kilowatt motor drive. Control communication and other auxiliary system may cost you something more on that. Additionally, which will include a controller board or a board which is going to control the inverter, interact with the battery, interact with the motor, sensor, connectors, and all those things will be there. So this effectively takes you to around 2.5 lakhs rupees for the material cost. When I say material cost, I will not say RMC only, the raw material cost. It will be a component of subsystem cost. But when I want to integrate them, naturally a few more things will appear into that. So the cost may come out to be around 3 to 3.5 lakhs rupees altogether, and that will be the net cost of the power drive which is required to be there. Now, these costs, when I talk about, I can't forget about the EV battery pack. EV battery pack is targeted to be reaching to $100 per kilowatt hour, but currently it is in the range of $150 to $50. These prices keep coming down. Okay, new technologies are coming up, and therefore we hope that in future we'll get a better option for the EV battery pack in lithium or non-lithium based batteries. So this cost, if I think about it, if I add it to the overall major components of inverter and motor, okay, this comes up to be around 6 to 7 lakhs rupees altogether. That means EV only to work with these major components together and keeping everything rest aside, okay, is going to be costly affair for any one of us to think about EV as our next car. So if you have noticed, other than very few commercially available versions of electric vehicle, okay, these are costing around 5 to 6 lakh or 7 to 8 lakhs rupees or so. Most of them are beyond 10 or beyond 15 lakhs rupees, and high performance vehicles are much beyond our reach as of now. So there is a quite a bit of need to reduce down the cost of it, okay, make it affordable. And this demand for the increase in the in-house R&D at academic platforms to develop the technology within the country. We are all, those are from the faculty side, those are basically belongs to institutes, engineering institute. They all know that there is a focus on to technology development or R&D within the labs, what we have it. And if you can do it, the cost can be significantly reduced. And while working on this domain, our group has really witnessed that the cost reduction can be significantly high, literally significantly high if you can do it at our level. There may be possibility that we can have initial challenges, initial difficulties of realizing a commercially available inverter and motors together, but nothing will stop us from coming close to that. So that's what is going to be guaranteed from our side. Being in the academic platform, we are good at R&D. We are good at doing research by understanding what has been happening around. So I'm sure we'll be able to come out with this design at very low cost. So development cost can be lower, RMC can be very low, and therefore the overall system design cost will be much lower. So if you can get EVs within 10 lakhs rupees remit with a good performance criteria, I think will serve the purpose of doing the R&D at institute level. In India, already there are premium institutes which are working with the industries and coming out with the solutions for that, and quite a bit amount of R&D is happening. So we should look forward for a significant reduction in the cost of EV. And once EV becomes popular, I think the technology will go on exploring very rapid rate, and this is expected to happen very soon. So I'm just presenting you the basic stages just to connect with what we are going to talk about. So basic stages in electrical vehicle drive design is going to include the vehicle dynamics to be accounted for, which will give me the total tractive force at wheel required. Okay, once I know that, okay, once I understand what is exactly I require to deliver to the wheel, okay, in terms of the tractive force calculation, which will tell me about the machine, the electrical motor to be used, what power, what torque, what speed I am supposed to use it for. So once I know the electrical motor specification, naturally the converter specification to be derived from there is becoming easy. Accommodating the efficiency of the converter, I can always start with the design of the converter. Finally, once I know the converter specification, once I know the motor specification, once I identify what performance criteria I am going to lay down, the battery specification can be derived by understanding the maximum converter rating and vehicle dynamics to be taken or accounted with a particular drive cycle, the nature of the drive cycle under consideration to be getting approved for it, to be taken into account while sizing the battery. So our stages are going to be: first, the vehicle dynamics to be evaluated; second, the machine specification to be derived from that vehicle dynamics analysis; third will be the converter specification; finally the battery calculation. There can be a reverse engineering can happen also in this case. We can go in the reverse manner and do the calculation also in that category. There is nothing, no harm in that. At the end, they should be suitable to each other. A motor cannot be having the higher power capacity than the converter. Otherwise, the converter will fail faster compared to a machine. So and so. So there has to be a proper relationship between each one of these components power rating and the total capacity required for handling the worst case scenario for the operation of vehicles. So I'm sure that based on your schedule which is given, the tractive force calculation, you must have gone through it. So I'm just repeating it for the sake of background creation out here. So FT is a combination, the total tractive force calculation it will be based on the basic components, that is rolling resistance force to be applied for overcoming rolling resistance, the aerodynamic draft component to be taken into account, the hill climbing component to be taken into account, the acceleration component in terms of linear as well as the rotational acceleration component to be taken into account. So these components, if I put together, that is the force to be applied on the wheel so as to start rolling out, and I can get the vehicle moving at a particular speed, particular acceleration, and climbing on a particular angle on the road. Okay. So this is a standard equation which is going to be based on the basic principles applied to the vehicle automobile engineering. They study this very much in the depth, but at the fundamental levels, this is going to be the way it will be calculated. So we get the equation in the form of the tractive force required in the form of some coefficient like mu rr. Okay, the mass of the vehicle will be accounted for that. Then we got a frontal area, vehicle frontal area. Then we got a CD, that is the track coefficient, the velocity of the vehicle to be assumed. That means the maximum speed which is required to be accounted for. Subsequently, we also talk about the inertia, moment of inertia to be accounted for, the efficiency of the gear system, the gear ratio, the radius of the tire, and so and so. So there are components which are required to be predetermined, and there are components required to be calculated based on your performance expectation of the vehicle is need to be done. I just want to confirm before I go ahead, if you permit me, that whether how to calculate this FT based on the parameter which I want to select. Is it been covered? If anyone can give me input, I can then proceed further accordingly. Anyone, even Aqleem sir, you can also help me out if you are there. How to calculate the FT based on, or rather the top speed characteristics and motor speed, the power speed characteristics of what is required. If it has been done, I'll not go ahead with that. I'll skip that portion and I'll go ahead with the inverter calculation. Is it been covered earlier in the earlier session? Hello? Anyone? Okay, so I'm not getting any input from your side. So what I'll assume is that possibly it is not covered. So what time I want to present to you a calculator. I think most of you might have done this earlier in your R&D also. So what basically we are talking about is that create a calculator either based on MATLAB or Excel or any other platform, and simply use the equations which have been derived for FT calculation. Specify your assumptions regarding a specific feature of the vehicle, and then estimate what is going to be torque speed characteristic and the power speed characteristic. So here you can see that we are talking about a context where we said that it is all going to be dependent on the rolling resistance, aerodynamic drag, hill climbing, the force required to give linear acceleration, and finally the angular acceleration which is required to be there. So mu rr is going to be dependent on the type of tire, the quality of the tire, and the road quality, and the interaction between these two elements together. Therefore, these numbers or these specifications are going to be dependent on certain selection of the types. Okay, so those calculation I'm just presenting you as a EV calculator so that we can get the idea about the motor's torque speed as well as the motor power speed characteristics. So here, if you see this calculator, I can see that I can select a road type over here as a part of dry concrete road or dry. In fact, we can choose even the snow out of here. As many as types you can categorize, as many as type of category of roads you can quantify the CRR. If it has been specified in some document, you can always list them out here. You can account for a gear ratio, what you want to go for it, either by reverse engineering or by the actual calculation. You can assume a particular wheel size of an electric vehicle, what you want to go for it by proper rim size or proper type of the wheel which is required to be accounted. So if I take into a standard wheel of say 255, 260, the specification which will be there, suppose I take that into account and I want to calculate the radius of that wheel together, the rim size of 18 or 19 inches together, we can identify the radius can come into this number 0.365, 0.39 or so. Vehicle weight will be dependent upon the type of vehicle you are talking about. Either it is a SUV or is it a sedan or is it a hatchback or what kind of EV you want to design. So typically these numbers are benchmarked against the available EVs, commercially available or the practices which are being used in automotive design. So this vehicle weight in terms of kg accounting for the curb weight and the passenger and the driver weight together, counting to total vehicle weight, can be inputted out here. Now, when I talk about various options available nowadays in the vehicle, I can have normal mode or economy mode or even the sports mode as a combination of it. We generally witness some of the vehicles will have economy mode as one of them and sports mode or city mode as a different types of modes available. I can define the parameter, I can define the limiting parameter for each one of this mode. In economy mode, I want the design to be, the control should be such a way that my minimum use of the battery will be there and maximum range I can get. Whereas in sports mode, I don't want to have any kind of constraint on the parameters which can be achieved with this particular design. Therefore, the maximum velocity, the maximum speed I can go for it, okay, and the maximum power available from the vehicle motor as well as the inverter can be achieved from there. Acceleration can be maximum in sports mode. Economy mode will have the lowest acceleration possible. So 0 to 100 km per hour can be reached within say 10 seconds or 5 seconds or maybe 20 seconds depending upon the mode we are going to. So once I select these specific parameters together, okay, and select the corresponding limiting factors on these modes, okay, I can simply go to the calculation and what I get once I select this parameter, what I get is a torque speed test. So we'll just go to the first one, the sports mode. In sports mode, you can see that these parameters are calculated based on my changes on the input side. I get a torque versus speed, okay, characteristic, and the power versus speed, the power of the motor and the torque output of the motor. So we can see that in this case, the torque of motor in Newton meter is reaching to around 430 Newton meter for delivering the sports mode operation, and it has got a base speed of around 3000 RPM. After that, we get a constant power mode coming into picture, and constant power mode is limited to around 140 kilowatt because we have put that limit in the sports mode. So this change in the torque, maximum torque and maximum power which we want to achieve in this category can be verified that if I want to go for a lesser velocity. So let me just try it out, maybe around 100 for this, rather 120 I place. So if I place 120, what should happen in case of sports mode is a slight change in the maximum speed it can reach to that. Okay, so I'll just go back to the previous number so that you can see the change now. Okay, you can see that here it reaches to around 11,000 RPM roughly, and when I reduce down the maximum speed, the speed of the motor is restricted to around 8,000 RPM. That means the maximum torque, maximum power, and the maximum speed of the motor, I can drag it or I can fetch it out from this calculation. And once I get that, I can decide the size of the motor. And that size of the motor now will tell me about how to size my power converter. So with this different types of modes, different types of operational modes and the constraint, I can always calculate what is going to be my top speed characteristics and where it is going to be limited. So these parameters at an individual designer level, we can tune it up as our required conditions to be achieved, and then we can proceed for the final calculation of the power inverter. So I'll take you, because I don't want to go into more details here. I just taken a brief look at what can be done in this particular thing in vehicle dynamics. And once I know the power, torque, and speed of the machine, and then I can decide the motor to be used for that. So the gear ratio and traction force is already calculated for that. So let us go to the converter specification. What it comes with, let us talk about that. Okay. So when I talk about these things, okay, I need to take few things into account for which the motor also will be changing, and the inverter size also will be changing. That is top speed, the maximum time to accelerate or minimum time to accelerate from 0 to 100 km per hour. Driving range. Driving range will basically tell you about the kilometer, the watt hour requirement per kilometer, and based on the drive cycle selected, it is going to change, and the capacity of the motor and the power inverter also going to affect that. So this driving range we have to estimate based on a few of the other factors to be taken into account. Other than that, these three criteria, we got the gradability, that means the slope at which we are going to go up, the curve weight of the vehicle, vehicle frontal area, and road types. This is how we accounted our design into that calculator. So there are many other factors also. We accounted only few of them to calculate the basic requirement of the vehicle drive. Okay, so let us take a first look at what my EV inverter is going to look at. Our focus will be EV inverter now onwards. We have talked about motor to be selected as far as the specification is concerned, from where it will come. Once you do that, I am going to look at what are the design considerations in the first place. How I am going to get challenged against any other type of inverter compared to an EV inverter. We were working on the design of inverter from 100 kilowatt to almost a few hundreds of kilowatt capacity. But when it came to inverter design for the EV, okay, even though it has range from 110 kilowatt to 150 kilowatt, the complete change in the form factor and complete change in the philosophy of design came into picture. So when we talk about EV inverter, there are few challenges required to be taken into account, so that the design becomes comparatively easy to understand and to differentiate from the existing knowledge of our inverter design. So if you look at this picture is very simple to look at when I look at from an electrical point of view. What I got is a battery. Sorry, I'll just place in full screen mode. What I can see is the battery pack, which is delivering the power to a DC-DC converter, elevating the voltage if required from that battery. Then it is going as a DC link voltage to this inverter. There are 6 switches. You can see 3 legs comprising of 2 switches in each of the leg. And for each one of the switches, or the IGBT or the MOSFET or electronic switches, there is a gate driver associated with that. And to control each one of these gate driver to drive these switches, I got a microcontroller board, and to have a feedback control loop, we got a motor current and voltage to be sensed for that. And to control the speed, I require the position or the speed sensing required. So if you look at this together, these are basically an architecture which is required to be put in a very small package, or enclosed package rather. It is not going to be an available for exposure to the external air or external environment, and required to be packed up to prevent any kind of dust entry or the water entry in that case. So packaging is a separate entity in the inverter design, but otherwise becoming a very small footprint, and including control boards, gate drivers, current sense, power devices, DC link capacitor, bus bars, protection devices, everything into a very small footprint is the biggest challenge. Because if I think of a 150 kilowatt inverter for a solar PV inverter, solar PV application, I can visualize a big half size, I can say, cupboard, okay, to be the size of that 150 kilowatt solar inverter. But I want to see that for the EV inverter, it is just like a double size of my laptop, okay, stacked together. Okay, that can be the size of my inverter possibly I have to design. So the whole thing changes because it is all packed up in a very small footprint, and all other issues will pop up because of it. So selection of all these components together and packing them together is one of the challenges which will come into picture. But if you look at the topology, if I look at the basic ingredients of this inverter, they are not much complex. They are it is very simplified version of the inverter. Compared to any other inverter in the industry, it is going to be complex comparatively. This is only a comparison I'm making for the sake to make you feel that yes, it can be manageable. We have done that at our end, so I'm just sharing my experience on that. Now, if I see it expanded view, I can see some of the additional components along with that. Okay, so on the right hand side, this has been taken from Texas Instrument. It includes a lot of components, a lot of subsystems, a lot of specific components requirement. If you see what is there, it's a power stage which is there at the center. Okay, which comprises of edge bridge inverter, which was shown in the previous slide. Okay, this is the heart of it's basically the power building block. I can say it is the one which delivers the power. But to control that edge bridge inverter, I require appropriate drivers, the gate drivers, and to interface gate driver with external world, I require a isolated drive, which is required to be interfaced with the external controller. Therefore, this particular thing has to be so close to each other that noise or any other external factor should not affect them as far as operation is concerned. To handle this, actually the gate driver and control interfaces will be a part of this red block which has been shown out here. Okay, this block includes all these first two components out here. Now to feed the power, the high voltage battery connection, which is shown on the right hand topmost corner, which gives the power to this half bridge converter in the 3-leg format. Okay, and that drives basically the motor at the end with the AC voltage converted by the inverter. Microcontroller and communication processor board, when I say this, will be the critical or most, I can say the one which is vulnerable to all the issues. Okay, vulnerable to all issues in the sense the switching transients, the kind of an high current pulses or noise, harmonics, whatever you talk about in electrical system or electronic system which will happening is going to be affecting microcontroller and communication board, which has been configured out here below this block. So there is a digital processing MCU core which has been indicated here, which includes the CAN and other communication interfaces also. To have the very good feedback control system implemented, we should have the really robust and accurate current and voltage sensors available. So I can sense the current and voltage which is given to the motor M, okay, which can be sensed and given with appropriate isolation, appropriate signal processing circuit to the core, that is the MCU, the microcontroller, and then microcontroller take the action to control the edge bridge inverter out here. Speed encoder is required for the speed sensing. Protection interfaces. As such, electrical protection is not directly implemented in the form of electrical protection switch gears. Okay, these are all based on the current and the voltage sense. These are all going to be based on the feedback which has been given to the microcontroller, and the most of the things will be handled by the microcontroller only. That means an intelligent device is going to control the equipment also, and it is going to protect it also. And that's the beauty of it, that I can literally protect an inverter against a short circuit without having a short circuit device in my system to break the circuit open. Okay, so I may not have MCB, may not have an fuse for handling the short circuit condition. It is only the microcontroller board which has been actually monitoring the current through that can protect the circuit, the power circuit, very fast way and very easily, and therefore these protection interfaces are required to be designed very appropriate way. Finally, to power up all these auxiliary circuits which are being shown here, we require auxiliary bias power supply, which has been derived from the 12-volt battery, which is being charged with DC-DC converter, which is shown in the first two slides. Okay, this gives you a complete overview about what an inverter will be comprising of. It has to have all these things, even though some of them will be boards, some of them will be the components, and if I integrate them together, it will become my inverter as a single entity. Okay, to have a feel about how it looks like, I had taken some photograph from some of the references, and What you are able to see here is a commercially available inverter in the market. Okay, and if I look at them, okay, these are all kind of an, I can say that they are properly sealed, and there's a proper IP protection which is being provided, and it will have the entry for the DC link voltage to be given. It will have the three-phase output coming out of it to drive the motor, and possibly it will have the entry for the thermal liquid, the liquid cooling segments, and finally for the communication. So these inputs are, you can see that there are tubes which are seen on the left hand side picture. These are the things which are basically allowing that entry into this box. Okay, if I open the box, possibly I can see something like this. Okay, there is a liquid cooled heatsink on which there will be switches which are mounted. What you are able to see here are the black one, the black next to the I can say the orange color studs. Okay, the bus bar which are shown out here, they are coming out from the current sensor. So there are three current sensors which are there. The PCB on the top, which is a bigger size PCB, which you can see here, the middle layer is the driver PCB for that reason, and on the top you got a controller board packed up together. So you can see the vicinity or the closeness of all these components when they are integrated together. Because they are close, there are a lot of things which can be avoided, and what are those things, or how they are going to impact us, we will discuss that very quickly. Luckily, I was able to witness this model, which you are able to see in a cylindrical form. Okay, this was there in our lab. This was manufactured by Tesla and was integrated with Toyota RAV4 model, EV model, and it is basically an motor with transmission gear and coupling in the electrical side connected to the inverter. So that kind of arrangement is there. So there is a motor on one side, there is a transmission gear with a single gear arrangement, and finally the inverter on the other side of it. So it is comparatively a much smaller package. If you look at the footprint, it was not really big thing. You just imagine a small cylindrical. I can say the unit is available to you, which can be held in a hand very comfortably and can be picked up very comfortably. So if you see that things opened up, we are opened up, and this was I can always thank Sani Electrical, which has given this product as well as project to us. Sani Electrical Engineering Works basically interested in working with this manufacturing of EV motors and EV drive. So we are working closely with them, and they'll be possibly will be coming out with their products soon. So when we open this unit out here, what we are able to see is a very small, tiny inverter. People are delivering more than 150 kilowatt at one go. Okay, 150 kilowatt of power in such a small package is something which is really fantastic to witness. Otherwise, we have seen very large size 150 kilowatt inverter in industry. So this is a different angle to be seen how the things have been packed up, and if you want to see videos on Tesla EV inverter, there are a lot of videos which are available, tear down videos which are available. So we have seen those also, and we have done it ourselves also. So this has given us complete insight about how the design can be really perfect, and how it can be so simple also. It is really simple as well as quite a dense populated components are which are there in the place. Okay, after looking at this picture and seeing the size of it, just imagine it's a size which is very small for such a large capacity. Required to have a more deeper look at the design consideration. So let us look at them at a time. So we'll be talking about few of them together today, depending upon the time limit to which I am going to stick to. So here you can see that we have power stage architecture, which is required by either single power module, half bridge module, power switches, DC link capacitors, which are required to be decided. So people work with all sorts of options available. Some of them use single power module, some of them use bridge module, and some of them use the parallel switches together. Okay, selection of DC capacitor is very crucial, and that took us a lot of time to figure out how to select and how to procure it. Major challenges happen there. Motor controller architecture, whether it will be a single controller or whether it will be a multi-controller architecture will be there, that also required to be answered. Gate driver design, even though it looks very simple in principle, but it is the most critical thing, because if that goes wrong, even if you are perfect in power stage or motor controller, nothing works fine for you. So gate driver design, even though it looks simple and I can say I can say low important kind of importance kind of a subsystem, but it is the critical thing which is required to be designed. Choice of sensors, comparatively simple to understand and can be easily selected because options available are less. Cable, bus bars, heat sinking, liquid cooling, EMI, MC designs, these are some of the other factors which will be also taken into account. Use of EV grade components is a mandate to make it compliance with the functional safety and other norms to be added to. And therefore, while selecting each component, including smallest resistor to smallest capacitor, for that reason, all the microcontroller also, we need to understand the compliance of each one of them, either AEC qualified or SL compliant component to be selected. Okay, finally, you may take a call on the functional safety requirement at the at some presentations in this particular schedule. We'll take look at some of them here, okay, and if required, we can have a discussion on the others. So power stage architecture, if you can witness, you can see three sets of picture. One on the left hand side, which basically talks about Infineon, the company which has basically driven most of the Europe market as far as the sub system or the component selection in the EV drive is concerned. This is my opinion. I have witnessed and I was able to understand that that way. So Infineon is the one which is leading. There are many other in the picture. Many other manufacturers are there. Infineon offers you the reference design in the context of hybrid pack versions, so version 2 here. Okay, it comes out with the single power module. What do you mean by single power module? All the six switches which you have seen in the basic inverter circuitry are packed up together and form as a single unit, which you can see in this particular lower picture. Okay, and this lower picture shows you it is an integrated module. That means they are stacked together. I cannot have one leg separate or one switch separate, and they need to be used together. And when I use them together, naturally my driver circuit, which you can see in the top picture out here, is been designed very cleanly and sits onto this connectors very straight way, and this is specific design correspond to this module. And on the top of that, there's a controller module designed by Infineon itself, which basically controls this EV inverter. The heatsink which has been designed has got a very peculiar design with the studs inside that, and allows you the larger cooling area. When it is going to allow the liquid to pass through, it will cool the whole inverter power module. Okay. At the back end, the blue color is the FCOS capacitor, specifically designed to suit this particular structure of the power module. Okay, they will have the studs coming out of it to sit into the DC connections on the one side and AC connection on the output side. So these are the AC connections, and on the back side where the capacitor is there, there is a DC connection for each one of the module connected to there. Some of the companies do not go for the single module, because if there's something goes wrong, one shot, if the one leg fails or one switch fails, the whole module is required to be replaced. So there is a possibility that I can have a loss on the financial side. So I'll prefer something like a single leg module. In principle, this is applicable to all inverter design. And single leg module, if I take, there are 2 switches, and if I want to stack a 6 switches inverter, I'll require 3 such modules to be used. So half bridge modules are going to be 3 numbers to form a 3-phase inverter. So just for the representation, I have shown you this particular picture of a stack, not for the EV purpose, but for the stacking 3 inverter leg module together and then connecting. There are more numbers also, and there is a DC link capacitor which are being connected out here. So this is not a EV drive, but this is something called the usage of the half bridge model. On the right hand side, what you are able to see is the cutout of the Tesla inverter. Okay, showing you the switches. Okay, the switches which are shown down here, manufactured by Infineon, they are there, and they are stacked together to form 1, 2, 3, 4, 5. There are 8 such switches and 8 on the other side. So there are 16 switches in parallel are connected of Infineon with 75 ampere capacity at 650 volt operational voltage. They are stacked together to form a one switch, which is there in this particular module on the single power module side. So this each stack will have total 32 switches per leg, and therefore 32 multiplied by 3 legs are going to be the number of switches which will be which are used in this particular module. So this is what one of the manufacturer opted. The other one can opt for the single half bridge module stacked together to form an inverter, or alternatively somebody can opt for the single power module on the way the Infineon has projected it. There are few other manufacturers which gives you this kind of solutions. Okay, so Infineon is not again the only one, but they are giving a good solution for that reason. So this particular arrangement, I need to select which one is my option for this, which one will be suitable, which I can take it up immediately and develop my control code, develop my inverter module, and I can start driving my motor very effectively. So this call has to be taken by the designer altogether. Okay, so each one will have a plus and minus both the sides available. If I go for the very compact design, possibly this can be the one on the Infineon hybrid pack 2 can be the way I can think of it. If I want to go for the modular design of it, I possibly will choose what the Tesla has selected. If I want to look at the lower cost version of it, I can go for the half bridge module also. Remember that cost of this each module, either the single power module or the half bridge module or the parallel switches or switching, is significantly high when I go for the design power of almost 100 to 150 kilowatt. They are really high unless until I really work on the proper design. Okay, this power module also includes the DC-link capacitor selection. You can see that you can witness EPCOS, which is now TDK. They have given a specific design to be useful for the EV drive. Okay, they are already written hybrid pack. That means they have designed this particular module especially suit the Infineon hybrid pack version 1 now. The version 2 also is available, and the mounting stud also will be suitable for that kind of a design. There are variety of other footprints or the kind of options available in this category. So many manufacturers are there. But the costs involved is very high. So when I select this capacitor, I need to see that they are film type capacitors, especially not the electrolytic, and they can give us a good ripple current capacity, which is required in EV type, and required to have very low value of ESR and very low value of what they call as equivalent series inductance, because inductance is going to play a big role as far as ringing effect is going to concern, and ESR is going to play a big role as far as the hitting effect which is going to be taking place, and the maximum current capacity or capacitor can pump in. That is how they are going to make. So selection of capacitor from the ESR and ESL point of view is very important if I want to choose. So this has taken us a lot of time, because in this category we had a difficulty to procure this, because these are specifically designed for a manufacturer of EV. It's not going to be commercially available very easily unless until there is a some standardized design available in this category. Okay, now let us see what that inductance ESL is going to play a part. Simple wire, a simple bus bar which has been used for connecting a DC connection from a battery to an inverter switch, or inverter switch from top level to a bottom level. If I am going to connect them together, the wire which has been used, or a bus bar which has been used, or any other element which will come in, termination which has been used, when it is going to carry current, it is going to have inductive property, and that inductance is going to play a part in creating a large kind of a transient phase or ringing, which is going to happen, which is referred as switch node ringing come into picture. And that you can see that operating voltage against the peak overshoot which occurs here, it is, though it is the damp oscillation, the first overshoot is going to determine how much is the voltage which may come across a switch, and unless until you select a switch of proper voltage rating, it cannot withstand this. So one thing is to avoid this ringing by minimizing these parasitic inductances is one possibility, or alternatively I have to use the switches with a higher voltage rating, which is also not desirable in that context. So right from using a bus bar, using their profile, the kind of cross section I am going to use it for, okay, the kind of a cabling or the wiring or the connectivity between the switches to motor, all these things are going to matter quite a bit when I design that. when we tested our first prototype, we have seen quite a bit of ringing out of it, and then subsequently we went on modifying it, and then finally we got a very comparatively much lower ringing available to us, in fact negligible, which gave us the confidence that now we can go ahead with the testing of electrical motor for the control. Okay, so the wiring inductances, the inductances of capacitance, the inductances of small other elements also, these are all going to matter important for us, and therefore required to be taken a due weightage for that. Okay. Motor controller architecture to be selected. Yes, we require to either go for single or multi microcontroller application. The one PCB which you are able to see is the one which is used in Ray4 inverter. You can see there are, in principle, there are 4 controller on board. Okay, one of them is TI DSP and other one is FPGA. They also use 2 DSPs in the on the board, so I can go for a single DSP or 2 DSPs or 1 DSP plus 1 general microcontroller, so and so combination. DSP or the digital signal processors, which is specifically used for the motor control, they cannot really deal with very easily with the external world. They cannot really handle the external world input very comfortably while doing the control. So you require to have the general purpose microcontroller, which can be in the form of FPGA, which can be in the form of general purpose microcontroller coming from specific companies like STM or Infineon. There are many options available in that category. So I can have a single controller, which is a dual core or 4 core controller comprising of maybe ARM Cortex plus DSP put together, hybrid version of it. Can be a single controller, or I can have a multi microcontroller chips available on board, and that can be used for my control of this inverter. So this is going to be a choice for the designer to select the one. Okay, you require appropriate isolation from external sensor inputs, GPIO high power inverter. Gate driver design, very specifics are there. We require to really be careful. I was telling you about the driver design, even though it looks simple, just give the pulse to the switches and make it on or make it off is what we generally assume in case of power electronics circuit design at the undergraduate level when we teach it. Okay, but it's not really so simple. Any voltage transient coming from switching of this converter switches, okay, we may trigger because of this capacitance which is connecting the drain to gate connection is going to cause us the switching of that switch in a non-desirable form, and that can lead to the failure of this inverter at a one go. There can be a shoot through and can cause a really disastrous effect, and therefore the appropriate path to be provided for the switching transient, the voltage change across the drain to source, to allow the current, as you can see in the no Miller clamp, the current which will flow from the one on the left hand side lowermost corner. Okay, a switching transient, the voltage which is going to appear is going to get bypassed through the CGD to the ground through this network, which will be taking a long time. And in this time period, if the switch goes on, if the positive transient comes in the picture, this switch which is going off will now turn on and will cause the a drastic current to be taken from the battery. So there are versions of drivers which are available which will have the Miller clamp. This effect is basically nullified as a Miller clamp to be provided, which bypasses this current very quickly and allows the transient to get damped out. So there are drivers which are available with the active Miller clamp to be utilized for the driving purpose, and quite a good solutions available from Texas Instrument, Infineon, and many other manufacturers. So we are currently working with both of them, Texas Instrument as well as Infineon driver ICs in this category. Isolation to be used, either opto-isolator or pulse, depending upon the bandwidth and depending upon the kind of isolation voltages you require. You can make a choice between the two types. Both are preferred in this category. And we generally practice the optocoupler, but the transformer-based designs also are possible. So photocoupler will get a pulse from the DSP or the controller, and that will drive the switches which are there in the inverter. So same way it will be happening here. Finally, it will drive the transformer. Transformer will drive the switches on the secondary side. So this kind of an interfaces gives us isolation. So anything happening on the high voltage side, high power side doesn't get reflected onto a microcontroller side. Otherwise, it will damage or disconnect at every frequent time and cause a trouble in controlling that particular drive. So there are concerns to be taken into account as far as the drive design is required to be considered, right? Rate of rise of gate current, rate of rise of voltage across the gate is also going to matter. Faster the rate, it will be better, but too fast of the change in the current also can cause a bad effect on that. But if it is slower, a slower turn off and slower turn on of the switches may occur, and that will cause the excessive heating of the switches and may result into increase in the temperature. The ringing which I was talking about is going to cause a dV by dt pickup on the input side and cause maloperation of the devices put together. Okay, let us come to the next point of selection is the sensor. You can see a picture. This is available in our lab. I just took a picture and I'm presenting here. What you are able to see is the Hall effect sensor on the left hand side. The black one is the voltage sensor. It is generally used in power system, but power electronics power system area. But in case of EV, a smaller version or the isolated shunt amplifiers are being used. Whereas for the center one, the blue one is basically the Hall effect current sensor used for the current measurement. Can be used to measure the current in each one of the phase, or it can be used even for the DC current measurement. All these components are required to be EV grade type, and therefore they require to be used appropriately. The one which is on the right hand side, it shows the bus bar with a shunt. Shunt is the smallest resistance which is going to cause a drop across it, and that voltage drop will again indicates us the current flowing through this bus bar. So I can simply measure the current through this bus bar by having a voltage drop coming across the shunt which is basically just in this cutout section which is there below the PCB, and that voltage is in millivolts. Very small amount of voltage will be dropping across it. That voltage is appropriately amplified and processed before it gets fed to the your microcontroller. So this output of this sensors are being fed appropriately at appropriate level before it goes to the DSP, and they require to be clean in the nature. Otherwise, the noise itself will be causing a trouble for the control. So the clean sensing, okay, appropriate signal processing, appropriate gain of the amplifier, and proper communication with the controller from the inverter side to back to the controller required to be very carefully done. Okay, the cost and number of sensors are going to be the one which will be limiting the kind of selection you are going to have it. Cost, LEM sensors are comparatively costlier, shunts are slightly less costlier. A number of sensors to be used, Tesla has used 2 sensors in some of the models. Rather than 3 what is required. Some of them use only 1, some of them use 3. So 1, 2, 3 are the numbers which are possible for the current sensing purpose. Okay, so cost reduction, I can reduce down the number of sensors if required. I'll come to very quickly on this prototype with courtesy from Saini Electrical. I'm not going to discuss much in detail because of NDA associated with this. I'll just brief you around what we have done with Saini and what Saini is helping us for that. This particular project has funded by the Saini for developing the specification what is given out here. Is 340 to 360 volt battery pack to be utilized with a motor of 110 kilowatt nominal power and 150 kilowatt 16,000 RPM motor to be developed. Saini is developing this motor and they have done a really excellent job to develop it at a really great cost reduction, and hope to see that product in the market soon. Inverter side we are working on so 200 kilowatt peak power and 150 kilowatt nominal power to be delivered, and we are working with the TI DSP. As a part of the first development, we have already developed the prototype at a lower specifications. This is a lab prototype. This is not a final version of it, and final version I won't be able to show you here. But we are working with the 58 kilowatt capacity peak power and 40 kilowatt nominal power liquid cooled inverter, and the size is meant out to be around 8 kilowatt per liter sizing is done, and we are now under testing for the this prototype, and once the final product is ready, we will be going for the final testing of this with the authorities. So this model, we started working with very fundamental understanding of the EV inverter, but then understanding procurement of each one of these component, even in thinking of the how the cooling will happen, how the bus bar structure has to be designed for, and what way they have to be assembled, what way they can be packed up. These are all going to be these were the things which will be like we witnessed. We have debated on that. We have tried our best to understand how it can be packaged into one particular entity. So with the experimentation, with the kind of trials, we understood finally how to pack it up, and the final prototype will be much different and much better as far as the footprint and the assembly is concerned. And all other components will be there. We have used some of the ready items out here. Some of them are assembled by us. So switches are on the right hand side of this converter, right and left hand side. You can see that picture is not available here. And this works at the first go when we tried and tested this without any much of the problem. Okay, the use of TI-DSP is especially because we have gone for ASIL compliant DSP controller. So we are sticking to TI here rather than any other controller manufacturer. Hope that our selection will be of use for us in the later part of the design for the final product. As the time given to me for this particular session is up to 4 o'clock, I want to keep some amount of time for question answer. I'll just wind up my discussion, not going to the exact details how it is done. I have the details available with me in the form of, I can say, the design Excel sheets from where we have done the final design with many of these components and sizing of the various subsystems, the number of switches, so and so. There are a number of calculations which have gone through it. But because of time constraint, it cannot be really completed in 1 hour or 1.5 hour time slot. I just want to conclude by saying what we are doing other than this, because EV inverter cannot go all alone. It requires a support from other entities, as we discussed in the beginning. Integration of that also need to be taken into account. So what we are doing at Charities in the EV domain as of now, we are also working on design of AC and DC fast chargers. Because once we get a battery pack for possibly for driving this EV drive, we require to charge the battery also. So we require appropriate chargers for that. Rather than buying, we thought we can develop it at our end. We also worked with the battery management system at fundamental level and worked for a few years in that category. Not professionally converted this product in the market. It will still take longer time. Research in the area of at the PhD level is happening at hybrid power source with a combination of battery and ultra capacitor put together. We are also working on the estimating the residual range to be estimated for an EV, because in India we have concern ki, if I got a battery which will just conk off in the travel, which I'm going to expect that it is going to last now for say 150 kilometer, and at 75 kilometer possibly it is showing me almost 80% of the charge lost. So what is going to be my mindset, whether I can understand within that 20% of the battery left out, charge left out, can I go to a level where I can at least reach to a nearest charging station. So residual range to be estimated in EV by understanding the EV inverter drive, EV battery pack, and EV motor characteristics. If I put all of them together, the EV complete EV drive put together, and their operational behavior, if I can estimate, if I can model it, and then therefore estimate my remaining range or residual range of what I can get from the available SOC of the battery, that will be useful for any driver to reach to the destination point appropriately. So this is what we are doing in that particular research. And finally, we are trying to work with the pedestrian recognition, so that when I drive the vehicle, if at all for some reason I require to get alerted on sudden appearance of pedestrian or other object, non-human object coming to your way, if you can identify it at an appropriate time and alert can be generated, I think then the accidents can be minimized. So these areas we are working for last few years, not more than 4 years as such, but slow and steady growth we have witnessed, and to an extent, I'll say that our team is still not expert. When I say our team, it comprises of the faculty as well as students working in our EV domain in our department. So when I put them together, okay, we still are trying to be an reaching out some fundamental details, some practical details about it. So we are not expert, or I am not expert in this category, but trying to learn a lot. Just like you, what you are trying to attend. Possibly we get small segments from each one of this kind of interaction. We can learn from each other's experience, and possibly we can reach out to the our target of indigenous design into EV domain as quickly as possible, so that India become independent on this particular technology development side. So that is my appeal from my side, that let us put all our efforts together so that the development in this segment can be fast, and we can witness a low cost electrical vehicle development at high quality performance available from the same EV to be available to Indian market, and then we should be in position to sell those in the other markets other than India very comfortably, and we can be the leader in this area. Okay. With these words, I'd like to thank all the organizers, Dr. Aqleem and Kamlesh, and all the team members. I also like to thank ATAL scheme for this particular sponsorship, and AICT for sponsoring this event. I also want to thank all the participants for patiently hearing me. If at all, if there are questions with associated topic, okay, I'll try to answer this as much as possible. If not, I can answer you later on through my email. Okay. So I'm stopping here, Aqleem sir.
Yes, I'll
Okay.
start the question answer session.
Yes, sure.
Normally, we have kept a system of keeping everybody mute during the entire session, because by mistake if somebody mic is on, then it creates disturbance. So
Okay.
participants, same way like other sessions, kindly raise your hand so that I can unmute you, or you can post on chat box so that I can tell sir the question and he can answer you all. So question answer session is open. You all can ask the question. Hello. Any questions from participant side?
There are possibly no questions also. That is
Ah,
also
yes.
one of the possibility. Actually, I can. Yeah,
Yeah,
there
there
is
is
one. Yeah.
one
Okay.
raised
Fine.
hand. Okay, it went away.
Yes, sir. Because name is not there, I won't be able to identify the gender.
Participant number 016. I am allowing you to unmute. No, sir, his hand has been lowered down.
Okay, fine. So more technical details can be only possible to share with a more number of hours, and with a permission from our sponsor to share with this. So I could not share much of the details here, but offline you
Participant
can
number
also.
016, you can unmute yourself. Sorry, sir, to cut you.
Yeah, sorry.
01, yeah, you can unmute. Hello, attendee number 016. You can unmute now, yeah.
16.
Yeah. You are audible.
For electric, for driving wheel, why gear is required? You can connect directly motor
Yeah.
to driving wheel.
Yes, sir. Actually, when we talk about connecting directly to the drive wheel, the issue is that the speed of the motor has to be lowered down. Because to get a wheel speed of say 150 kilometer per hour, okay, I require to drive the vehicle, drive the motor possibly at much lower speed of 1500 or 2000 rpm. And driving at that speed, the size of the motor becomes bulky, and naturally the weight and other things also will increase. So if I increase the speed of the motor, the size and the weight of the motor can be reduced down. So simply by having a single reduction gear of typically of a gear ratio of 10, 9.73, 9.83, these are the numbers which are used. It becomes easy to connect to the mechanical system. At the same time, operating the motor at the high speed gives me the advantage at that time. So the control and other things becomes easy for to operate. That's the one of the reason for which it has been done.
Sir, why Tesla car is so popular?
Why Tesla car is so? Hello?
Is very
Can you
popular in US. Very popular. That
when
means
sir, go ahead, please.
any technology they have used. We are using all lithium-ion batteries, different same powertrain drive. Why the Tesla is so much demand is there? Why popular? Even Modi has also visited that plant.
Yes, possibly we can witness Tesla in 2021 in India, and everybody is fascinated. I can just put my views on this. Tesla, even though we're not from the automotive background, and comparatively there are many players which are working in the EV domain for quite a long time, literally quite a long time, and they were having the EV cars in the market for the long time of presence. Okay, Tesla has picked up it well. The reason possibly is that they were not biased, okay, and they got the advantage not being from the background of automotive. They were able to develop everything on their side, okay, at one go, and possibly given the integrated solution put together with everything almost optimized. The kind of feature, the kind of the performance what they gave, okay, was not really available with rest of the world. That is one thing. Okay, cost wise they were comparable in the sense, if we compare the other manufacturer at that time, they were comparable at. So it was not the cost factor according to me was available with them, but it was the complete integration put together with the complete different thinking of coming out with the solution has given them the advantage. And still, if you look at it, the kind of a battery pack they are working, or look at what the control options they are given, the whole thing has turned out to be the much better feature than any other car. If you compare the cars available from other rival manufacturer and very senior, I can say in the industry, they were not coming close to the performance what Tesla has given in a short time. But now I think other companies are picking up, and Tesla will have tough time to compete with them, and the market share, retaining the market share subsequently will be challenging task unless and until Tesla comes out with a very low cost solution for that reason. Okay, the others are catching up very quickly, and some of them will even keep the Tesla behind. I'll not name any one of them because these are all the news available to every one of you. I think you can understand to whom I'm referring to. So the one which appeals, one which appeals the common customer, I think, is the one which gets sold faster. So Tesla has appealed, and I think EV, when it named, or EV, when we talk about, the first thing comes to mind is Tesla, and Tesla was not the pioneering company in this category. So still it has taken a lead on that. Thank you, sir.
Any other question? Yeah, I think, sir, there are no further questions.
Okay,
So I'll just conclude the session over here. Yes, with the formal vote of thanks to you, sir. I would like, on behalf of my team, that is the organizing team of ATAL FDP on electric vehicles and Department of Mechanical Engineering, I would like to thank you for coming over here and taking this
Thank you
session.
very much.
And yes, sir, and sharing your knowledge. And personally, yes, I would like to thank you in front of everybody for being behind us, supporting us and guiding us to organize this event, rather, I would say, because the inputs that you had given, based on that, we have done the entire scheduling and sequencing of the speakers. So thank you very much for that also, sir. And yes, we know in the college you are always there to support us, to help us. So thank you once again, sir.
Thank you,
So
sir.
shall I
Thank you very
conclude the
much.
session, sir?
Sure. Thank you very much.
Thank you, sir.
Thank you.
Okay, participants, the feedback link has been shared in the chat section of the WhatsApp group. And tomorrow morning, there will be a session on stress management by Art of Living. So please don't miss that session. It will be there from 10 to 11:30, the first session. This is as per the mandatory requirements of ATAL FDP. So tomorrow morning, we'll be meeting at 10 o'clock for the session on Art of Living. And there were some questions or some queries regarding the test and mode of test. So test would be conducted on MS Forms, and it will be an MCQ type of question. The detail of the entire test process I will be sharing in the morning after the morning's first session. So we'll be meeting tomorrow. Thank you. Good night and bye.